Welcome to solverfy.
Okay, this problem is asking us to propose a mechanism for this reaction right here. Okay, so I see that I have an epoxide, and that has an alkyl bromide chain, and that is going to undergo a reaction with my CH3O-, aka methoxide, and then we're going to have the formation of this product and this side product. Okay, so my methoxide is a very strong base. Okay, it's also considered to be a nucleophile. And because it's a super strong nucleophile, and we have the presence of this epoxide, it's going to go ahead and attack on the least hindered carbon. So this carbon right there, and I'm going to open up my epoxide. So the whole reason that we open up this epoxide in the first place, as opposed to potentially attacking that carbon, releasing that bromine in an SN2 reaction, we're going to do this SN2 reaction in which we open up our epoxide. And the reason behind that is because epoxides, specifically three-membered rings, have a lot of angle strain, right? Because if we have an sp3 hybridized carbon, we would like to have the angles between the bonds be approximately 109.5 degrees. But if it is locked in this conformation right here, then it's in that three-membered ring. And three-membered rings have a bond angles of much less than 109.5. So that's why we have to open it up so that we can relieve the tension in those bonds. So the product of that is going to be this, in which I have my OCH3, and then I have the carbon chain, and then up here I have my oxygen, and then I have the remainder of my chain. So that's going to be looking like this. Okay, and then as we can see here, we have my OCH3 and my O-, those are going to be trans to each other. That's because every time I open up a ring with a nucleophile, I'm going to have the corresponding substituents be trans to each other. Okay, and that's on opposite sides. Okay, and again, we have to form this product right here. So proposing the mechanism for that, all I would have to do is, instead of protonating this oxygen, I'm going to have it behave as a nucleophile. Okay, it's going to behave as a nucleophile in an SN2-like reaction, in which I attack the carbon connected to my bromine, because that carbon is considered electrophilic, because we can actually go ahead and make this bromine leave as a leaving group. Okay, so as we can see here, we formed a five-membered ring. Let's see if it's a five-membered ring here. So we have 1, 2, 3, 4, 5 atoms in our potential ring. I always label my nucleophile in this case as atom number 1, and then my electrophile as atom number 5, or at least the last of the series. Okay, so that's going to form this, in which I form my five-membered ring, and then this is atom number 1, 2, 3, 4, 5. Okay, so here's 1. I have the oxygen connected to carbon number 2 and carbon number 5, so that's done. And then on carbon number 2, I have the connection to carbon number 3, but I also have the connection to this chain right here. So I'm going to write that out. I have that CH2, and I have this OCH3. Okay, and then I have the rest of my chain, and then the bromine was before connected to that carbon number 5, but because I made it leave, it's not connected to it anymore. So it's just like this. So that would be my final product, and then my bromine would be my side product because I had that leave. Okay, so part B is asking us, or showing us that we have the formation of a six-membered ring. Okay, it's asking us to show that. So let's go ahead and write that out. So I'm going to have my same starting material as before. Oh, I'm going to go ahead and duplicate that, move it down here, and then let's go ahead and react that with my OCH3. So if I were to react this with OCH3, again, that's a strong nucleophile. Okay, if it were to make a six-membered ring, then going back up to here, then we would have a situation in which this O- would not be considered to be 5, or at least 1, 2, 3, 4 carbons. It will not be considered 4 carbons away, because otherwise it would have to make that five-membered ring. So we have to have that oxygen 5 carbons away, and then that oxygen would be the sixth atom. Okay, so we have to have a situation in which that would occur. So this OCH3, as opposed to opening up the epoxide over there, it's going to attack right here. Okay, and I'll show you what happens in that. Okay, so I'm moving the electrons up to the oxygen, and it's going to result in the formation of this product. I have my oxygen up there, and then I have my carbon, OCH3, and then I have the connection to my alkyl bromide chain. Okay, so as we can see, we're at a different scenario than the previous one, because right here I have my oxygen on the right side, and on this side it's on the left side. Okay, and then OCH3 on the left, OCH3 on the right. So this is a different formation of product, but this is the mechanism for the formation of the six-membered ring. Okay, because as we can see, if I were to move my oxygen, the electrons from it, if I'm going to move them onto this carbon, that will be a formation of a 1, 2, 3, 4, 5, 6-membered ring. Okay, and that is what this problem is asking us. So we're going to have my oxygen be up on top, six-membered ring, like that. Okay, so this is carbon number 1, sorry, atom number 1, 2, 3, 4, 5, 6. Okay, let's just go along our bonds and determine what's connected to what. So oxygen is connected to carbon number 2 and carbon number 6, so that's done. Carbon number 2 is connected to carbon number 3, that's done. Carbon number 3 is connected to OCH3. Okay, and then 4, 5, 6, okay, we're done. And then we just have my bromide as my leaving group. Okay, so that will be the structure of my 6-membered ring. Okay, and then part 6 is asking us, why is this particularly unfavorable? Why is the 6-membered ring formed in such low yield? And that is because, back up to here, we had the OCH3 attack on to this carbon. That carbon is more hindered than this carbon, right? So the whole purpose of having an SN2 reaction, in this case, is that we want to attack the least hindered carbon possible so that we can have a bimolecular transition state in which 2 steps happen simultaneously. If it attacks on this carbon, that's a little bit more hindered than this carbon. So it would be a little bit more difficult for that nucleophile to come in and attack that carbon. So it's just a little bit more hindered than it would be if it were to attack this carbon. Okay, so that's the whole entire reason why.